we are now going to see two applications of derivatives, physical applications. We have already seen geometric applications and other things. For example, we have used derivatives to find tangents to curves at some given point. We did those things, but now let's see two physical applications. The first one is it involves pressure and volume of a gas contained in a closed container. Say a gas is in a closed container and it's maintained at a constant temperature T. In that case, its pressure P and volume V are related by a relation or formula like this: P equals nRT divided by V minus NB minus AN square divided by the square of the volume, where these quantities A, B, N and R are constants. We have to find the rate of change of pressure with respect to volume. Actually, you are most probably already familiar with a special case of this formula. Maybe this you did not see this one itself, this is a general one, but you are at least familiar with the case where A and B are both 0. If A is 0, this second term vanishes. If B is 0, here the denominator becomes V. So the formula reduces to P equals nRT divided by V, or PV equal to nRT, ideal gas law, and that equation is called ideal gas equation. And there you actually also know what these constants are. R is your gas constant, N is the number of moles. So these are things you already know from physical chemistry. But anyway, let's now find this rate of change. We have dP dV. Okay, so P of course is that, but instead of writing P exactly like this, we are going to write the second term here slightly differently, in a form that will be easier for us to differentiate. The first term of course we will keep as it is. An square times V to the power minus 2. What shall we do after this? I mean, what type of laws shall we apply here to differentiate this thing? Here, of course, you have to use the quotient rule, quotient law. There is no getting around that. Here, we can use the power law with negative exponent, which is available to us. Because if you apply the quotient rule, it takes some space. So let me write the thing like this. So in the quotient rule, you have to square the denominator times. Now let me write the rest from here. And then you do not differentiate the denominator first. You keep it as it is and multiply that by the derivative of the numerator, and then minus. In the quotient rule, you have a minus sign in between. You keep nRT unchanged and then multiply that by the derivative of the denominator. So this is the derivative of this, minus. Now A and N are constants. So by the constant multiple rule, they just stay like that. And if you differentiate V to the power minus 2, it becomes this. The exponent comes down, and then here the exponent gets reduced by 1 or you subtract 1. Alright. Now, this term will vanish because n, r and t are constants. Well, n and r are constants, and remember we are keeping the temperature constant. So the temperature doesn't change even when volume changes, and that's why this derivative is 0 minus nRT times differentiating V we get 1, differentiating NB we get 0. So this is our first term. Here minus and minus will give us plus, so 2a n square times v to the power minus 3. That means this term vanishes and we have minus nRT here. nRT divided by the square of v minus nb plus 2a n square divided by v cube. So that is the rate of change of pressure with respect to volume in a gas contained in a closed container and where temperature is kept fixed. Now, if your equation was the reduced one means if it was the ideal gas equation, then what will happen to dP dV? That's not a part of the solution, but we can just see what it will be. In that case, the pressure looks simply like this in terms of volume. And here you can just substitute A equal to B equal to 0. Doing that, you get minus nRT divided by V square. Okay, so that's a special case. Note that from the point of view of mathematics, this is almost nothing. No, I mean, we have been doing just this for quite some time now. We are just differentiating functions. Here also we have differentiated a function and we have found its derivative. So what's the big deal? Mathematically there is no big deal, but physically this is very important. Important to the chemist or the physicist who may be using this thing. Okay, so from the point of view of application it will be important, but mathematically it's actually rather dull, truly speaking. And one more thing is that although, let's just consider the simple case here. You have the ideal gas equation and you find the rate of change of pressure with respect to volume. Alright. In experiments, this is not found first. Usually, this is what we find first. For some reason, it's easier to conclude from whatever data you may gather in your laboratory during experiment, rates of change than the actual quantities. Okay, it's easier to find the rates of change and relationships among the rates of change. For example, this is an equation involving a rate of change or derivative. Such equations are called differential equations. At one point of this book, we are going to study these equations to some extent. We will study them enough so that we can see some very interesting applications like this one. Okay, so in physical sciences, in chemistry or wherever else. The goal is to solve the differential equation. What that means is that you will obtain an equation involving a function p. Here p is a function of v. The other quantities are constant. So p fundamentally depends on v. As v changes, p also changes. But when you have an equation like this, you don't immediately know what the exact actual relationship between P and V is. This is also a relation, but it relates V with the rate of change of P with respect to V, not to P directly. So this is a differential equation. Solving this differential equation gives you the actual function, at P as an actual function of V. That's what scientists do. What they do is that they conduct experiments which involve some kind of quantities, and they want to know how these quantities are related to each other. And they formulate from whatever theory they may have for their study differential equations, and then they try to solve these differential equations. And the solutions they get will give you some kind of rule or law like ideal gas equation or something else. That's how the process goes. The next application is to medicine. This is a fortunate or unfortunate, I won't say, thing that people who do not like mathematics, see, there is nothing bad to dislike mathematics. I don't believe that everyone has to like mathematics. No, this is a personal choice. No, if you dislike mathematics, fine. But the problem is that those who dislike maths, those who do not want to deal with quantities, equations, they tend to gravitate towards biology or medical sciences for some reason, which is very nice. But every now and then you will see that eventually you have to come across some equation or some quantity. The moment you measure, it's not just in biology or it's actually everywhere. The moment you try to measure something, the moment quantities get involved, some kind of equation will inevitably appear. And then at least you have to deal with it at a rudimentary level. So this is one such situation. I don't think it's at a rudimentary level though. The body's reaction to medicine. When you take medicine, almost always there is some kind of side effect. So can that be measured? Yes. The relation let me just take down the problem first. The relation of the body, no, not relation, what, that doesn't make sense. Reaction the reaction of the body to some dose of medicine. You are administered some kind of medicine, your body reacts in a certain way. Can sometimes be represented by an equation. Of this form. People who work in medicine, they came up with this equation. Again, by doing some kind of experiment, measuring things and then seeing what the relation is. R equals m square times C over 2 minus M over 3. This is of course not an arbitrary relation where C is a positive constant and what are M and R, and M is the amount of medicine. Okay. Absorbed in the blood. All right. If the reaction, now R is not anything fixed. R, in place of R, several things can be considered. If the reaction is a change in blood pressure, then R is measured in millimeters of mercury. Okay, change in pressure. But R can mean something else also. If the reaction is a change in temperature. Oh, okay, yeah. I mean, whatever changes, R is that change. I think it's not just simply change in blood pressure or change in temperature. I think something else also can be considered here. So these are just two examples. So what is it? Is if the reaction is change in temperature, R is measured in degrees and so on. Okay, so these are the quantities. M is the amount of medicine in the blood, C is the positive constant, and R denotes some kind of change in some quantity of interest, temperature or blood pressure. Find, yeah, that's what we want to know, what to do. The derivative of R with respect to M. And then the authors say this derivative as a function of M. I mean, of course, if you differentiate R with respect to M, ultimately it's again a function of M. That derivative as a function of M is called the sensitivity of the body to the medicine. In section 3.6, we will see how to find the amount of medicine to which the body is most sensitive. If you think of how this possibly may be useful to people who create some kind of drugs, medicinal things, if they know this, then they can control the amount of medicine that can be given to someone in a specific situation. Because otherwise, if this R goes beyond danger level, of course, that much amount cannot be given. But how will you know that? If you do not know this, you won't really actually know how much to give. what to do, how to create that drug. So to do that kind of thing, these things are necessary. So let's now find the derivative or the rate of change. In this case, it's better to call it rate of change. We have, or if you want, you can start the solution like this. The sensitivity is dRdm, and then you can write. Let us first multiply this thing by m square, because that way it will be easier. So that then looks like this. With respect to mc over 2 is constant, so we write that first, minus 1 over 3 times mq. So this is a rather easy thing. Differentiating m square will give you 2m. Mathematically it's very easy. And differentiating m cube gives you 3m square. So the sensitivity comes out to be this, Cm minus m square. That's just what it is. Again, from a mathematical standpoint, it's something trivial. But from a medicinal standpoint, it may be something really very important. I don't know. People who are experts in that subject, they will know. So let me just end the video here itself. There are some other exercises also in this section. So we will see in the next calculus video how much we can cover. Because there are so many exercises, see, the aim is not to just simply rush through them and do as many as we can in a very short frame of time. That's not the aim. The aim is, of course, to carefully solve these exercises and learn along the way. And tomorrow we have, as usual, our linear algebra. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.